So this first slide here just shows you the difference between scientific notation and standard notation, which is sometimes called long form. What we have here in scientific notation, the things we want to watch out for is that there is only one number in front of the decimal. So this value here is going to be less than 10 but greater than 1. We also have a multiplication symbol, and then we have times 10 to some exponent. These two values are actually completely equal, and what this means is if I take 5.32 and I do times 10, times 10, times 10, times 10, times 10, this would come out to 532,000. Same value, just a different way to show it. In scientific notation, we have a value that looks like this, and I kind of explained that on the previous slide. So this value that comes before the multiplication symbol is less than 10, but greater than 1. We can have an exponent here that is positive or negative. So the reason why we have scientific notation is because in science we have a lot of things that have very, very tiny values, like the mass of a proton or the mass of an electron, and then we have really large values like the size of a planet. And so we need a way to express numbers without having to write down all of these zeros and losing digits just by forgetting to write something down. So one thing that becomes helpful is to remember that anytime you have an exponent and you're trying to figure out if the exponent should be positive or negative, is to think about the value of the number. If the value of the number is greater than 1, and I'm talking about the long form, the original form, if it's greater than 1, then the exponent will be positive. If the original value of the number is less than 1, then the exponent should be negative. And one of the things that makes scientific notation a little bit different in chemistry than in when you probably learned it for the first time is that in chemistry we now know about sig figs, and so you have to retain the number of sig figs as you convert to and from scientific notation. So here's our first example. With this example here, we want to first understand where the natural decimal point is. The natural decimal point is going to be right over here, even though it's not written in, but you know it goes there. And we are going to want to move the decimal point right over here. So we are going to count how many times that decimal place is going to move over, and it's going to move over 1, 2, 3, 4, 5, 6 times. And we then have to decide if our exponent will be positive or negative. Since the original value is greater than 1, this is a very large value, we're going to have a times 10 to the positive 6 exponent. Notice that I also retain the number of sig figs here and here. We have 1, 2, 3, 4, 5, 6, 7 sig figs, and here I have 1, 2, 3, 4, 5, 6, 7 sig figs as well. This slide asks you what's the difference between this number, and there's no difference between them. It's just that this is expressed in scientific notation, but the value of the two numbers are exactly the same. If we wanted to convert this value to scientific notation, here's what we would do. We would see that the decimal place is placed in right after the first 0, and we need to decide where to move the decimal place. The decimal place is going to move right here between the 5 and a 2 because we want just one number in front of that decimal place. And when we move it here, it's going to move over 1, 2, 3 times, and when it moves over 3 times, we have to decide, is this going to be times 10 to the positive 3 or times 10 to the negative 3. And we are going to go ahead and call this times 10 to the negative 3 because our original value of the number is less than 1. Anytime we have a small value for this number, we want to have a negative exponent. If you're not quite understanding what I mean by large value and small value, think about a dollar. If the value is worth less than a dollar, less than 1, then you would know that the exponent needs to be negative. If the value is greater than a dollar, then you should know that the exponent needs to be positive. So I want you to go ahead and press pause and try to convert each of these into scientific notation now. When you're ready, go ahead and hit unpause because I'm going to keep going with the video. For letter A, what we want to do is we want to move the decimal point from here to right here. And when we do that, it's going to move over 1, 2, 3, 4 times. We see this value as greater than 1, therefore it's going to be a positive exponent. So 6 times 10 to the 4. Notice that the number of sig figs have been retained. There's only one sig fig in this value because there's no decimal here. Therefore, the scientific notation value has to also have one sig fig. For letter B, I see 2 sig figs, and I want to make sure my scientific notation value has 2 sig figs as well. I move the decimal place from here to here. And when I do that, I have a positive exponent because this original value is greater than 1. And in this case, I can put times 10 or times 10 to the first power. Either answer is acceptable. For this value here, I'm going to move the decimal from here to here. That's moving over 3 times, and this value is greater than 1, so a positive exponent. And finally, I'm moving my decimal from here to here because I need one number in front of the decimal, and when I do that, I'm moving it over 2 times, and we have times 10 to the negative 2 exponent. Next thing I want you to do is I want you to press pause and convert this into scientific notation. If you've now hit unpause, we're going to move our decimal from here to here, and we know that this is going to be a positive exponent because this is an extremely large number, and we move it over 1, 2, 3, 4, 5, 6, 7, 8 times. And when we move it over 8 times, we have times 10 to the 8th power. I've also retained the number of sig figs. I have 1, 2, 3, 4 sig figs, so here I have 1, 2, 3, 4 sig figs. All of these zeros at the end of the number are not considered significant because there is no decimal. For this value here, we're going to go ahead and hit pause as you try this out. And if you've now hit unpause, we're going to move our decimal place from here to here. Another thing worth noting is how many sig figs there are in this value, and there are 1, 2, 3, 4, 5, 6, 7 sig figs, so our scientific notation needs to have 7 sig figs, and we move the decimal over 4 times, so here is how our value looks. It is very important that you recognize that these zeros on the end do need to stay with the scientific notation value. That's what makes this a little more difficult in chemistry, scientific notation, because it's not a new topic to you, because we have to remember to retain the number of sig figs. For question 3, go ahead and hit pause and try to convert this into scientific notation. And if you've unpaused now, we move the decimal over from here to here, and that's a movement of 1, 2, 3, 4, 5 spots. This is going to be a negative exponent because this value is less than 1, or it is less than $1, worth less than $1. And that's what our scientific notation looks like. So now we're going to go backwards. We're going to convert from standard form from scientific notation into standard form, but the rules haven't really changed. So if I have this number here, 2.48 times 10 to the 5th power, and we want to convert it to standard form, we're going to move our decimal over from here, and we're going to move it 5 times. We want to move the decimal to the right because this is a positive 5, meaning we want to create a large number. So we move our decimal over 1, 2, 3, 4, 5 times, and when that decimal moves over, we can't just leave the number like this. It actually changes its value, so we need to fill in all these extra spaces with zeros. The last thing we want to do is make sure that our number of sig figs have been retained, and so we have 3 sig figs here. We want to have 3 sig figs here, so the way that we show this number with only 3 sig figs is by removing the decimal point. So when we remove that decimal point, this value now has 3 sig figs, and it has those extra zeros to show that it represents 248,000, the same as this scientific notation value represents. We want to now convert this into standard form or long form, same thing, by moving that decimal over 6 times. When you move it over 6 times, we're moving it over to the left this time, because moving it over to the left means we're creating a number less than 1. That's what this negative indicates. And we move it over 1, 2, 3, 4, 5, 6 times. And there's the decimal moving, and we fill all of these spaces with zeros to show the value. We want to make sure the sig figs are correct. We have 3 sig figs here and 3 sig figs here. So we know our number is correct. Here's our final value. Now, whether or not you put the 0 in front of the decimal, although it's proper, it's not required, and it doesn't change the number of sig figs.